So on 18, it said the integral from negative a to a of a minus the absolute value of x dx, right? So all of those in that section, on that like 11 through 20 section, all of those were about drawing the picture, finding the area. So, just to summarize where we're at here, we started with this definition of definite integral, which is finding area underneath the curve. We've given a couple of examples why we might want to do that. One was distance. If you have a velocity graph, the area underneath there is the distance. How many people are in physics or took physics? Let me take it with Miss Fisher. Somebody was saying, the first block was saying something about that. Anyway, but I think you do something like with that. I think in physics a little bit with velocities and distance and those kind of things. There she is. We thought you went on another vacation. Yeah, seriously. After coming back and seeing this, it'd be like, okay, I'm going to come out. All right. So the area under a velocity graph tells us the distance traveled. So that might be one reason to do area under a graph. The other one we talked about was yesterday was average value, right? You've got this function. It's got a bunch of different values. Maybe we had a bunch of continuous readings of the temperature throughout the course of a year. And so you got this graph that goes up, goes down, goes up, whatever. What's the average temperature for that year? We're talking about climate change, things like that. What's the average temperature? Well, you got an infinite number of readings, let's say, if it's a continuous stream. So you model it with some function. You want to know the average of that. Okay, well, we just showed a formula yesterday. Do the area under that graph, divide by the width, gives you the average value. So we got a couple of reasons already why we might care about the area under the curve. And then at the beginning of the year, I don't know if you remember, but I told you that one of the ways calculus came about was, back in the day, in the Isaac Newton days, there was, the people that were rich in those days, a lot of them were either royalty or property owners, right? Well, sometimes that was one and the same. And the property owners, and so how valuable your property was a big part of your net worth. And so measuring the land was a big deal, and a lot of times it was odd shaped, with rivers and odd boundaries. And so finding a way to measure these areas of kind of odd shapes was an important thing to do, and that was one of the reasons that that this came about in calculus. Interestingly enough, so finding these areas right now until today, and what we do today and tomorrow. There's not a lot of areas we can find. I mean, we're stuck with geometry areas. They've got to be triangles, trapezoids, squares, maybe circles. And the only way you can get that is if you get lines, like linear equations, And so most equations, parabolas, sines, cosines, those kind of graphs, we don't have a way of doing those right now. So we've got to go a little farther with this. So this homework and yesterday's homework is really about just getting comfortable with the notation of a definite integral, a fixed piece of area, and calculating that. And then we want to move on and see how we can do these other ones. Okay, so we have a lot to add to it today. All right, so anyway, back to this one. So basically we need to draw a picture of this. Okay, so I think it helps to flip this around and write this way. Because now what is this? This is a V graph. What's a negative do? Flip it down. What's a plus A do? Shift it up. So if we were going to draw a picture of this, it would simply be the V graph pointing down and shifted up A units. So that would be A right there. Now since it's a slope of 1, it's down A and over A. So this point right here is going to be A, and down 1 and over A. So this point right here is going to be negative A. So therefore now this makes sense. So now it's the integral, or the area, from negative A to A. So it's this area right here, which is the triangle. So what is the, so that's 1/2. What's the base?
2A.
That'd be A and A, so that'd be 2A. And then the height is A also. So 1/2 and 2 cancel, so the answer is just A squared, like that. Okay, so the key is drawing it. The key is getting a draw. And the same thing is true on 20. 20 is just a half circle, radius R, and so you would have, basically you'd have very much the same picture, but it'd be a circle. This would be negative R to R. So 20 is just asking for the area of a half circle, radius R. Well, that'd be 1/2 pi r squared. 1/2 pi r squared. Okay? So, finding area. So, on 11 through 20, so very important, to do one of those, we simply just have to draw a picture and see what the shape is. Okay? The only one we know how to do right now is geometry, shapes. Okay? All right. So, what else? Well, let's go to the book then. What about the book problems? 62. Okay? Yes. Anything before 62? 57. Okay? 57. X plus cosine x. Okay, so let's look at that. So it says the integral from 0 to pi halves of x plus cosine x dx. Now they told us over here that the integral from 0 to pi of sine x dx was what? 2. Now that's actually an interesting piece of information too, because that's true. I mean, I think if you type in your calculator, you try it, it is 2. Now think about that. I think drawing a picture is really the key here. Again, I said that the other day when I went around, and some of you didn't have pictures drawn yesterday on yesterday's homework on some of those problems. Okay, but here's the sine graph from 0 to 2 pi. So from 0 to pi, we'd be talking about that area. So it's kind of interesting to me that comes out an exact number, right? That area right there is 2, and it is. Now, think about that. Here's what's important in this problem. Sine and cosine, aren't they basically the same graph? Just what? Just a shift, right? They're exactly the same graph because they share all those same values, square root of 2 over 2 and 1/2 and square root of 3 over 2, right? They go up to 1 and -1. They're just shifted. So doesn't that tell you that every hump in the sine and the cosine graphs are 2? Yeah, they are. They are. Okay, or -2 if they're below the x-axis, right? So that's how we do this.
Kind of a quick question on 56. Now, if the sine and the cosine, why is it not 2 on 56? Why is it pi on 56 if it's 2 for sine? Like it shifted over like negative pi halves and pi halves. Like
and you're saying the answer book said it was? My answer book says 2. And is that what you got from here? Probably. You said the answer said pi.
I don't know. I probably was looking at the wrong one.
Okay. Right. Yes. Yes. No, you're exactly right. You're exactly right. Because that's exactly what that one would be. Here would be cosine from negative pi halves to pi halves, and that'd be one hump. And so that should be exactly the same. That should be 2. Yeah. Yeah. So that your reasoning's perfect there. So bring that on to 57. What can we do in one like this? No. That's the key. Remember the formulas that we have. Split it. Split it. That's what we got to do. Well, we only have a couple of forms we use. Split it and then pull out a constant. We talked about that, right? So what you want to do on this one is you want to go, okay, 0 to pi halves x dx plus 0 to pi halves cosine x dx. That's the key. We want to really get in a habit of doing that because when it comes to derivatives, we didn't really write that out. We didn't, we said do the derivative of this, then do the derivative of this, whatever. Well, here we say do the integral of each one, but it really helps to actually write it out when you're doing integrals. Okay, so what is this one? Well, let's draw a picture. Well, I already got cosine, 0 to pi halves. So 0 to pi halves would just be that part. Well, what's that? That's got to be 1, right? Because of symmetry and everything else. That's got to be 1. And then what is this? Well, how are we going to get this? Draw a picture, right? This is just like number 18 or 17 or any of those ones in the packet. We need to draw a picture. What are we going to draw a picture of? Well, right, but y equals, good, y equals x, right? This is our function, so we're going to draw y equals, x, okay, and goes through the origin, kind of, and then it's from 0 to pi halves. So over here is pi halves. We're going to have a triangle, okay? So the base of the triangle is pi halves. What's the height of the triangle? Also pi halves, because it's y equals x. So we plug an x in, and we get the same y. So it's going to be 1/2 pi halves times pi halves, right? 1/2 base times height. Well, what is that? Pi squared over 8. So pi squared over 8 plus 1 is our answer. That's how we get it. Okay, now we're only able to do that because this created a geometric shape. It created, this x created a triangle. And that's how we can do triangles. And that's how we can get the area. If this would have been x squared, we can't do it. And we only were able to do the cosine because they told us this, right? They told us this, and so that's what allowed us to do that. So our goal here over the next several days is how could we have done number 57 without all that information? How could we have just found that area, right? And we're going to come up with it. All right, so 57. Okay, let's go to 62. So 62, now this is one that unless, I mean, I like it. It's a good problem. It's not a big deal in the long run here, but you had to go back into the reading. You had to go back into the section. There's an example very much like it, okay? But it didn't say look at example whatever. So I'm guessing you did look back in the section. Something we don't do very often, and and I don't make you do it. So why would you, right? But if you look back a couple pages back, they talk about this. They talk about bounding an integral. Okay, bounding an integral. So here's an area we don't know. So pi 6, so let's look at this. This is pi halves, which would be 3 pi 6. So if I divide this into 3 parts here, this would be 1 pi 6, this would be 2 pi 6, which is pi thirds, and then 3 pi 6, right? So this would divide up evenly. 1 pi 6, 2 pi 6, 3 pi 6, like so. Okay, and so the area from pi 6, which would be here, to pi halves, so we'd be talking about this area right here. Okay? Now, we don't know what that area is. We know the whole thing is 2. We learned that in the last problem. But we don't know what that part of it is. So what they said in bounding an integral is we can use what we learned with derivatives. We can find the minimum and the maximum. So if you have an integral, a weird shaped area you don't know, you can find the lowest point on the graph and the highest point on the graph and draw rectangles, and you know that the area has to be between those two. Now, this is more useful from a theoretical standpoint than a practical standpoint, okay? But it's a little bit of good trig review, and it's just not bad to talk about. Okay, so here's what they're saying. They're saying take the lowest point in that interval, which would be here, and draw a horizontal line, and there would be this red area. Now, what is that red area? Well, it'd be this height. What is this height right here? It's what? Sine of pi 6. You take pi 6 and plug it into sine. What is sine of pi 6? It's 1/2. Sine of pi 6 is 1/2. Okay? So this rectangle here is 1/2 the height times the base. What's the base right there? Pi thirds, isn't it? Because it would be pi halves, which is 3 pi 6. So this would be 3 pi 6 take away 1 pi 6. That'd be 2 pi 6, which is pi thirds. So 1/2 times pi thirds. So height times width, that is what? Pi 6. Oh, that's that. So we know the blue area has to be more than that. The blue area has, because what we did is we took the lowest point and said, what if it stayed that all the way across? Well, we know it's more than that. And so the area's got to be more than pi 6, okay? And then take the maximum point, which is this point right here, and draw straight across. And then now look at your black area. Okay, well, what's the height of this rectangle? 1. And what is the width? Pi thirds still. So we know the black area is pi thirds. Oh, there you go. So that's what that problem was about. Okay, so we know the blue area has got to be somewhere between the black and the red. And the black is pi thirds and the red is pi 6. So that's how we know it's got to be. And that's all that problem's about. Okay, so really not a big deal going forward. This is a big deal. Being able to split apart, be able to draw this picture, calculate areas. That for sure we want to be able to do. Okay, yeah. 71. Okay, what about 66? Let's talk about 66 real quick. I don't think it was too hard, but let's talk about it, then we'll talk about 71. So on 66, it said the average value from 0 to 1 was 2, and the average value from 1 to 3 was 4. So I want to go over this just because I want to make sure we use those formulas. Okay, so the average value from 0 to 1 would be this formula. The average value from 1 to 3 would be that formula. Okay, and they told us that was 2 and 4. Then they say, what is the average value from 0 to 3? Well, the average value from 0 to 3 would be integral from 0 to 3 divided by what? 3 minus 0, right? That's the average value formula. It's the integral from a to b divided by b minus a. The integral from a to b divided by b minus a. Okay? So, that's what we're trying to find. Well, we already know the 3 down here, so that's easy. What we need to find is this right here. We need to find the area from 0 to 3. Well, how can we get that? How can we get that? Yeah, the area, yeah. So in other words, multiply the bottom over there, right? Because what you have is the area from 0 to 1 plus the area from 1 to 3, right? So that's using that other formula that we talked about. The area from 0 to 1 plus the area from 1 to 3 should be the area from 0 to 3, right? So if I take this 1 and multiply it over here, well, that would just still be 2. So the area, so this area is 2, right? This area here is 2. And then here you got a 2 and you multiply it over there, you get 8, right? So this area must be 8 right there. So the area from 0 to 1 plus the area from 1 to 3, that would be 2 plus 8, that would be 10. That's got to be that area right there. That's got to be the area from 0 to 3. And then divide by 3. So 10/3 would be your answer, your average value from 0 to 3. Okay, 10/3. 3 and 1/3. All right, let's talk about 71. So 71 is a little bit of a foreshadowing for things to come in the future. Okay, so they give you these two functions. X plus 6 is the f function. X cubed is a g. Doesn't really matter which is which here. But so I graphed those poorly, evidently. But I've got those two graphed. Now, part A, in chapter 7, we're gonna do a lot of problems like this. This concept in this problem is called area between the curves. We're supposed to find the area between, and they give us 3 regions, or 3 curves to describe the region. Now, we'll get really good at this because we'll do a lot of these problems. But in part A, we'll do a lot of problems that sound like this. Sketch the region in the xy plane bounded by the curves y equals x plus 6, y equals x cubed, and the line x equals 0. So you'll graph those, and you'll say, okay, it's got to be bounded by this, and x equals 0. Where's that? The y-axis. So it's got to be bounded by these 3 things. Well, clearly that's this region here, right? So one of the things you'll be learning, and one of the things you'll be having to do, is identify the proper region, right? Because up here would be a region that's bounded by the 2 curves, but it's not bounded by x equals 0. So that's why they had to throw the y-axis in. Okay, so it's just this region right here. So it's this black, right? It's this black region we're trying to find. Well, that's not any region we've talked about. The only areas we've talked about is between a curve and the x-axis. So that's not a region we've talked about. So part B then, they say, find the area, or not find, but express the area using integrals. So it's like your packet where they just want you to set up the integral, but you don't have to find it. So any ideas? I mean, I know what the answer is in the back, but I mean, I don't know if that makes sense to you about how.
Find the area below the straight line.
Okay, so let's take the line. Okay, let's just stop right there. I think I know where you're going. So we don't know how to find a region like this. We only know how to find a region under one curve and the x-axis. So she's saying take the line, which would be at this red area, right? I think is what you're telling me, right? And that would be the integral from 0 to 2 of x plus 6 dx. That would be the red area right there. Okay, keep going.
Well, I didn't know how to do that geometrically, so.
Well, you don't, we don't know how to do it geometrically. That's why it said express the integral, but don't find it.
Okay.
Go ahead.
Subtract
So-
the area under the x cubed curve.
Okay, this area here would be the area under the x cubed curve. So that would be the integral from 0 to 2 x cubed dx. So to get the black area, we would do what? We would subtract those two. And that is what they're talking about. Now, it said express that using integrals. Okay, well there we did, two integrals. Now, I would say to you though, that we could actually write that as one integral. Right? Because remember our rule right here, where we split these apart? Can't you do that in reverse? Can't you put them together if they're split apart? And we certainly can. So we could actually take that and we could write that as integral from 0 to 2 of x plus 6 minus x cubed, which wouldn't really need to be in parentheses, and we could rearrange that, whatever. That's actually one integral, which actually would be its own graph. We could take that and graph that, call that f, right? We could graph that. It would look different than this picture, but it would have an area under it, and guess what area it would equal? That black area, right? So we could take this then, graph that as a function, look at its area underneath between it and the x-axis, and it would be the same number, the same area as that black. A different region, but it'd be the same number. Remember, definite integral is just a number. A definite integral is just a piece of area, just like a slope. Just like f prime of 3 is just a number. It's a slope. Same thing with area. Yes?
So that's how we solve these things.
Shh. I don't know, maybe. I don't know yet. We haven't got it. There's some hints to it. Maybe. I don't know. We'll see. All right, get your notes out. Yeah, I mean, just type it in like that. Yeah, it'll just pop up. You know, Vanessa's question was on her calculator. So right here, you could type it in as two separate, or you could type this in, right? And that's in that. Well, here I got it up right here. That's in here by the 9 where the derivative is. I think I did that the other day, didn't I? So 0 to 2. Oops. So if we're just curious on that one, we go 0 to 2, and then what was that? X plus 6 minus x cubed, and then dx. So that black area was 10. That black area was 10. Yeah, it just does it. That's pretty cool, right? I mean, and there will come a time when we get into chapter 7. I might have mentioned this here. Maybe it's just the other class, but there will come a time when we get to chapter 7 where the hardest part of the problem, or the key to the problem, is setting up the integral, setting up the proper integral that will answer the problem for us, and then you just get to type it in your calculator. And sometimes on the AP test, they don't need, especially on the no calculator part, you get a lot of those problems where they just say set up but do not evaluate, right? Just set up the integral. They want you to set up the proper integral, okay? And so we'll spend a lot of time working on that. But I'll be honest with you, it's way easier. Yeah, I know when I say that, it sounds like our story problems in chapter 4, which could be pretty hard. The hardest part was setting up the thing we were trying to maximize and minimize. Some of those were darn hard. To be honest, I think experience tells me that when we get into these, they're not nearly as hard, right? That stuff we did in chapter 4, setting up, was harder, I think way harder than what we have in front of us, okay? So that's good. All right, so let's go, I'm sorry, back to, where are we at? Here. Okay, so in your notes, so if you remember, you don't have to write this part down, but if you remember where chapter 1, when we were first talking about slope and derivative at a point, we made a table. Remember, we did the sine graph. We talked about sine, and we looked at it, and we said, okay, and I think I parceled it out around the room and had some of you do some different slope calculations. And we looked at 0, and we picked 2 points, right? We looked at some of these points. We picked 2 really close points. Remember that? And we did a slope calculation. And here we got like 0.999 or something, almost 1. And then we went to pi 6, and we got like it was like 0.86 something. And we went to pi fourths, and we got 0.7 1 or something like that. And we went to pi thirds, and we got like 0.5, really close to 0.5. And we went to pi halves, and we got 0. Remember that? If you look at it, it makes sense. It looks like that's about a slope of 1, and then the slope's getting a little less, and then of course here we got a slope of 0, right? And then what did we do? What did we do with these? We plotted them, remember that? And what did we get? We got the cosine curve, right? We plotted them, we said, 0, 1, okay, and then 0.86, then 0.7, and then 0.5, and then 0, and we plotted them. It's like, oh, you're kidding. It was like one of our first aha moments, oh wow, and some of you fainted, which was fine, and that was okay, but it was like, oh, you're kidding me. The slopes on the sine graph are actually square root of 3 over 2. That's what this number is right here. Square root of 3 over 2, and this is root 2 over 2. The slopes on the sine graph are actually cosine values. Exactly, not just approximately, they are exactly those values. And it's like amazing, what a connection. But we said, okay, so what we've done is created a new function. So if this is f, we called this, that was our f prime. That was our slope function. And so we made a big deal about how when you graph f prime, you're graphing the slopes of f. F prime is a plotting of the slopes of f. So what we like to do is the same thing for area. Right? We want to do the same thing for area. We want to plot the areas of f. Here's the problem. For slope, it was easy. At this point, you have a slope. At this point, you have a slope. At this point, you have a slope. Does it work that way for area? At this point, do you have an area? Where do you have area? Between 2 points, right? So how are we going to do a function where we have the area? Well, here's what we're going to do. We're going to take, and let's say this is our function f right here. We're going to take and just fix our left endpoint somewhere. Let's call it little a. Okay, so this part you can write down if you want. So we're going to take, and you might label this area function. That's what we're working with here. That's what we're working for. We're trying to create an area function much like we created a slope function. Now the slope function was simpler. The notation was easy to understand because it was just at this point we get a slope. At this point we get a slope. And then we plot that, we call that f prime. So the notation's a lot trickier here than it was with slope. Okay, so that's one of the hurdles we have to overcome is the notation, because that tends to get in our way of our understanding of this. Okay, so that's why I'm approaching it this way. I think the approach we're going to take here is going to help. Now, and me, it's not going to be confusing probably at some point, but again, I think back to when I learned this in high school, and I had a great teacher in high school, and it was off the way the books at that time presented this stuff. And that's this section right here is one of the reasons I like this book, maybe more than any other section in the book of how this is presented. When I first got this book and started teaching out of this book, it's one of the reasons I keep using it. That's why they're all recovered and they're falling apart and everything, and I don't want to get new ones. But the way it approaches. It's the way it approaches this. Because when I first started teaching this book, I'm like, oh yeah, now I get it. Seriously, I've been to college and I even taught out of another book, and I got this book. And I'm like, I get it now. So hopefully you realize that a little bit too. But so we're just going to pick some left endpoint, okay, A, and then the right endpoint we're going to call X. Now I'm going to draw these little arrows in here because imagine that then as being able to move and change because X is our variable, okay? And so we're going to call this area function A of X, okay? We're going to call this area function A of X, capital A of X. And X is going to be our right endpoint. So that way now, since we fixed the left endpoint, Now we have a function. So if you think about this, right? The x is right there, you get an area. You move the right endpoint to a new x, how many areas do you get? A new one though, right? So it is a function. In other words, for every input, there's only going to be one output, right? Move it to a new right endpoint, you get an area. Move it to another right endpoint, you get an area. Now, it actually could slide, this right endpoint could slide and be on the other side, right? Okay, that's fine. It would just be backwards. So remember the last couple days I said you probably been wondering why would you ever go backwards? Well, here's a case where you might go backwards. What if x is over here? What if I wanted you to find a of -1? A of -1 would be the area from A to -1. Well, that'd be back here. So it would be going backwards, right? And so the area would be opposite, right? Opposite whatever it was. All right, so how would we write that as an integral? Well, it'd be the integral from, what would be down here? Little a. What would be up here? X. And this is little f, right? So this would be little f. Now, here's where notation gets kind of fuzzy. And so I want to talk about this a minute. So right here, we'd be tempted to write f of x, right? But we can't. Why not? We're already using x. We're already using x to be this. So we can't use x to be the points on here because x is this point. So we can't use x two different ways in the same problem. So we have to use something else. But that's okay. So usually we use t. But remember you guys had a question yesterday about the ones with the letters. Remember, we talked about w squared is a parabola. T squared is a parabola. U squared is a parabola. Z squared is a parabola. It doesn't matter. F of U, F of W, F of German short hair, F of T, they're all the same. They're all the same, right? So it doesn't matter. So the key is this is little f, okay? But we can't, if we're using an x up here, we can't use an x down here. That's the key, okay? Now, again, I'll talk more about that as we go along, okay? So you understand this. Okay, so this x here matches with this x up here, but we can't have x anywhere else. All right, so that's going to be called an area function. All right, so as we pick different right endpoints, we'll get different areas, and then of course we can plot that just like we did with the sine graph. Okay, so let's look at a situation like that. Okay, so I've got a picture drawn here. You don't have to necessarily draw this. You can if you want, but it doesn't really matter. But a lot of the times over the next several weeks, you will hear me referring back to this picture. I'll be talking about the orange area. Okay, so I'm thinking back to this picture here. So what I have is a little f function. So little f would be, here it is right here, x plus 2. Now you might be saying, wait a minute, I thought you couldn't use x. Well, yeah, I could use x there. But if I was going to write this as an integral, I don't have it inside my integral. So here I could write that as f of x equals x plus 2. But if I write this as an integral, here's my left edge, it's at 3. So this would be 3 to x. And then what would I put in here? I would put f of t, but what would f of t equal? F of t would be t plus 2 dt. So I would write it like that. Okay, I would write it like that. So understand, the little f line is x plus 2, but when I put it in the integral, I can't put x plus 2 because I'm using x for that. So I have to do something else. Well, t plus 2, well, that's the same. T plus 2, W plus 2, Z plus 2, X plus 2, they're all the same. Okay? So we just have to use something else. Usually we use T. Well,
What if we just keep using f of x and don't use x for the top? Just use number of letters.
we could do that too. Matter of fact, I've seen that on the AP tester in a multiple choice question. I mean, here's what I would be calling this. I would call this A of x. Okay, so I'll get to your question in a second. So I would call this A of x. So let's say I ask you to find A of 4. If I ask you to find A of 4, where would you put a 4? Well, right there. And where else? Right there. So if I ask you to find A of 4, I'm asking you to find what? The area from 3 to 4, right? So if I say find A of 4, we want to put a 4 there, we put a 4 there. Now what if I would have put an x right here? What if I would have put x plus 2 here? And I told you to find a of 4. You say, oh, you put a 4 for x, you put a 4 for x. What would you want to put right there? You'd want to put a 4. But you can't put a 4. We don't want a 4 there. You see what I mean? That's why that can't be an x. So Cody's question is, well, why don't we use x here and then use something else here? We could. I've seen this written a of t. Well, if you're going to write a of t here, then you'd put a t there, and then what do you have to use here? Well, anything but t, right? Anything but t. Now, I think it's confusing, and why do we do it this way? So the answer to your question is, why do we do it this way? Because this is a function we really care about. That's the one we want to have the x in, I think is the answer. Okay, the area function is what we're focused on, so that's where we want the x to be. This is just the function that we're doing the area under. So we don't care what letter is there. Okay? All right. Don't worry. That will hopefully clear up as we go. But I think it's already clearer than what a lot of books do. All right. Anyway, back to this. So what I've done is I've plotted that point. Here's the point. Okay? X is right now at 9.19. And the orange area is 14.53. So I have plotted the point X and the area. That's what this point is right here. Now, as I drag this to the right, what's going to happen? What's the A going to do, the A point? It's going to go up, isn't it? Because I'm gaining more area, right? What happens if I come back to the left? It's going to come down because I'm now losing orange area. I have less and less area, so the A graph is going to be coming down here. And then how much area do you have right there? What's the area from 3 to 3? We talked about that yesterday? 0. Now, what is this area? This is negative area, isn't it? Because we're now going backwards. We're now doing the area from A to X. So from here to here, that's backwards, so this is negative, and look at our area over there. It is negative, so the A point is still going down. Now, right here, we're still picking up, and you're going to hear me say this a lot, again, over the course of the week, so I'll talk about sliding the X, and I'll talk about picking up area, and I'll talk about losing area, right? Well, right now, we're picking up negative area, aren't we? So that graph is going down. All right, once I get to here, though, what starts happening? I start picking up what? What kind of area is this now? This is now positive area, isn't it? Because we're going backwards, so it's opposite. So this is positive area. So we're picking up positive area. So look what the A graph does. Starts going back up. Starts going back up. Now right here, you got what? 0 area because those two are canceling each other out. Okay, but you keep going, and you're picking up more and more positive area, and there it goes. Oh, now some of you had some crazy idea. I don't even remember what you were saying earlier. But, you know, what's interesting to me is I noticed, where did this bottom out? Down here, right there. You mean there was a local minimum right here when this graph switched from negative to positive? I bet that's just coincidence. That can't be. All right, so moving on. All right, so now keep that in mind just a little bit. Check your calculators. Hopefully you're getting this in a second. You'll be getting this document here. Okay, you can go ahead and just open it. If you already have a document open, it might say, hey, do you want to save it? Just say no. Whatever old document you had, you can just say no. And then you can just click open on this. Yes?
Is there something for
When the dot crosses the x-axis?
like the line,
I don't know. Let's look at that. Was it? I don't think so. No. What that would be is that the area, I think that would be where the area is the same as the y value on the line, but I don't know that that's anything important. Yeah. All right. Oops. Okay, so on to this. Everybody getting this open up right here? Okay, hit Control and right arrow, and that'll take you to the third screen. And you've got your worksheet there. Okay. All right. Now, here we have the integral from, if you look on your paper, it says the integral from 0 to x of 1.5 dt. Well, what we've graphed is the function 1.5, which is just a horizontal line, right? And if you can, now I'm probably going to do most of the work up here because I know it's hard on your calculators, and we'll kind of answer these together, all right? But can you grab this point down here? I think you arrow over it, and if you hit the center button or hit enter, it'll go to like a close, and you'll be able to drag this point. So you get kind of the hand, and then if you grab it and hold, it'll be a fist, and you can drag. Are you able to do that? If you're not, don't worry too much about it. Once you get the closed fist, you don't need to press. You can just kind of move with your finger, move across. Okay, but all right, see what we're doing there? All right, so now let's go back to the worksheet. It says complete the table. Okay, so when x is a 1, what's our area? It's the area from 0 to 1. What's that area? 1.5. Oh, because it's a rectangle that's 1 by 1.5. Okay, then we drag it over one more, and what's our area? 3, right? 2 times 1.5, and then drag it over again, 4.5, then drag it again. So it's very much like the picture I was just showing you, that as I drag the x to the right, what happens? I pick up a chunk of area. Remember the word chunk. It just seems to fit when we do this. We pick up a chunk of area, right? And then we move it over one, we pick up another chunk, and we pick up another chunk, and we pick up another chunk, okay? And so you fill in your table. All right, so now it says, if x equals 0, what is the area? So let's go to question 2. What is it? 0. Yeah, that'd be the area from 0 to 0. So that's 0. Okay, for every 1 unit that x changes, how much did the area change? Every time x changed, the area changed 1.5. If you were to graph the ordered pairs, x and then the area, what would the graph look like? What would it look like? It'd be a line that would go over 1, up 1.5, over 1, up 1.5, which of course is slope, isn't it? Okay, so you go to the next screen, and they ask those questions, which we just answered. Okay, and then you go here, and they give you a chance to actually plot those points that you just wrote down in your table. So what did we have? 1 was 1.5. What was, and then just hit enter. What was 2? 3. Next one, 4.5. Next one, 6. Next one, 7.5. So I know I'm going kind of fast, but that's what you have in your table up there, right? 1.5, 3, 4.5, 6, 7.5, right? They're just going by 1.5 every time. And you look over here on the graph, and sure enough, what happened? So, right, control right arrow gets you to this page. You plot those, and sure enough, there we go. That's what our area graph. So that's just like the other thing I was showing you with the orange area. Just plotting the point of that area, see what that looks like. And that's what we call our area function, right? It's a new function, just like we had a slope function. It was the derivative. It was y prime. Well, this we're just calling the area function. We'll call it big A. Big A, right? We'll call it other names too, but big A, right? But there's no symbol like a prime or something. It's the integral symbol, actually. Okay, I mean, but again, that's where the notation's a little tricky. All right, next page. So now we're going to change. Oh wait, you got some other questions. Okay, so question 5. What does the graph look like? Well, we just said it was a line. Was it what you predicted? Yes, of course. We were right on top of it. Okay, if you changed it from 1.5 to 0.5, what would the graph look like? If instead of going over 1 and up 1.5, it would go over 1 and up 0.5, because every time we move the dot over, we're going to pick up a chunk of area, but it'd be a smaller chunk, right? It'd be a smaller chunk of area we would pick up. So the graph wouldn't go up, and the graph wouldn't go up as steeply, right? Okay. And don't worry if you get all the, I mean, you know, yeah, be thinking about it, writing it down helps. We're not going to hand this in or anything, so just, we want to understand the concept of what's going on. Okay, so let's move to the next strain here that's important is 2.2. And I'm going to move my little dot back here to 1 if you want to do that. But now we've picked another little f. 1/2 t, or t divided by 2, or 1/2 x. We can think of it as 1/2 x as the graph, just a line. Okay, slope of 1/2. And we're going to do the area under that. Okay? All right, so I don't want to go too fast here, but okay, we're going to do the area under that. So if I start back here at 1, what do I got? It says 0.25 is my area. Well, let's check that out. We got a base of 1 and a height of 1/2, right? If you put a 1 into this, you get 1/2. So 1 times 1/2 is 1/2, and then you take half of that for a triangle, and that's 1/4. Oh, sure enough, 1/4. So we got an area of 0.25 right there. Okay, so you can put that in your table, 0.25, right? Top row of your table, 0.25 is the area. Okay, now let's move that over 1. Now we got a triangle that is 2 across, and what would it be up? 1, because you put a 2 in here. 2 divided by 2 is 1. So it's a 2 by 1 triangle. So 1/2 times 2 times 1. Well, that would be 1. So now we got an area of 1. Okay, now we drag them again. Okay, and what do we got? We got 3 on the base. And what do we got up here? What's the y value here? Put a 3 into there. 3 divided by 2 is 1.5. So we got 3 times 1.5, that'd be 4.5. Half of that, 2 1/4. So we got an area of 2 1/4. Now, what do you already notice is happening? I'm starting to answer some of the questions below already. What do you notice is happening? We went from 0.25 to 1 to 2.25. What's happened? Is it growing by the same amount? It's growing by bigger amounts, right? Well, why? Well, every time I drag this 0.1, what do I pick up? Remember the magic word? Bigger chunks. Remember, magic word. I said remember the word chunk. It just seems big. In this picture here, every time I go over 1, I pick up a bigger chunk of area than I did before. So I'm picking up bigger and bigger chunks as I move along. And so that area number in our box is going up bigger and bigger. So I go over here to 4, and I get what? 4 for a number. I go over here to 5, I get 6 1/4, and I think that finishes up the table. So if we go to the questions, if x equals 0, what's the area? Still 0. Why? Well, because there's no area. Duh. Explain why when x increases by 1, the value does not increase by the same amount every time. Why doesn't it increase by the same amount every time? Bigger chunks. There you go. There's right, bigger chunks. Perfect. Bigger chunks. Every time we move over 1, we're picking up bigger chunks of area. So it's not going to go up by the same amount every time. Okay? Is the graph linear then? The area graph going to be linear? No. It's got to be concave up, doesn't it? Because it's increasing at an increasing rate. Remember when we learned that about concave up? We're picking up big, so it's increasing, but it's increasing faster and faster. So we're picking up bigger chunks of area. Okay. So what happens when you get one that crosses the x-axis? So let's arrow. Oh, we get to actually put them in now. So let's go ahead and put these in here. You don't have to if you don't want to. That's fine. I'll just do it here real quick. So if I put these numbers in, kind of fun. You can see the dots. You can see them going, and you see our area. And sure enough, doesn't it look like it's concave up? Right? It looks like these dots are going up, but it's starting to curve. And it looks like it's not going to be linear like the one was before. Okay? Concave up. All right. So, moving on to 3.2. All right, so now we got this graph. Okay? Now, we're not going to plot a table of these values or anything, but we're going to talk about this whole negative positive business. Okay? All right. So, it says to drag the point X along the x-axis, observe the area value. So, at what value of X does the integral's value begin to go down? When does it begin to decrease? Well, right now it's 1.76. I move it here, and what happens? I pick up a positive chunk of area, but a smaller one than what this first one was, right? So I pick up a chunk of area, so the area graph would be doing what? But it would be going up, but it would be concave down, wouldn't it? Because I'm picking up a smaller chunk, so it's going down. Now, the next step I take over, I pick up what? A negative chunk of area. So therefore, that area graph's got to start going down, right? And then what happens? I pick up another chunk, bigger negative chunk, so it keeps going down, bigger negative chunk, still bigger negative chunk. So not only that, it's going down, but going down faster. So still concave down, right? So I apologize for anybody watching the video here, but so it was going up, and then it's going down, 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 until there. Because now I'm going to start picking up what? Smaller negative chunks. Now there's still negative chunks of area, right? So I'm still picking up negative chunks of area. So this graph is still going down, but leveling off. We have a change in concavity right there because we went from picking up bigger and bigger negative chunks to now picking up smaller and smaller negative chunks. So the area is still going down because I'm picking up negative area. Okay, picking up negative, smaller chunks until here. And now I'm going to start picking up what? Bigger and bigger and bigger positive chunks. So the area graph is going to start going up, 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 up like that. So isn't that interesting that this point, this inflection point, corresponded to that point there, a local minimum, and isn't it interesting that this local minimum here corresponded to that point right there? Huh. Wow. I find that very, very interesting. So, moving on, to the questions. So, 12. At what values are the integrals? Is the integrals value decreasing? Well, here's my picture. It was decreasing from, what was it, 2 to 11. What were the integrand at these values? What's the integrand? That's the little f. The little f was negative. The little f was below the x-axis. When the area was decreasing, little f was below the x-axis, or negative. What is true when the integral is increasing? Or at what values? 0 to 2, and from 11 on. And what is true of the integrand there? Positive. The integrand was above the x-axis, positive. What's the smallest value of the integral? When did the area get the smallest? That was at, I don't remember what the value was, but it was right here at 11, wasn't it? And what happened with the integrand there? Right here. The integrand, that's when the integrand went from negative to positive at that point. Is the connection between the location of the minimum value and the sign change of the integrand from negative to positive one that you've seen before? Yes. Yeah. So, to sum it up, Emily and Cody, the area function under the curve F is the antiderivative of F. In other words, if we have in our chart F, F prime, F double prime, where can we put big A? Big A can go right there, right? Big A was the antiderivative of F. Big A can go right there, which of course that's where we put big F usually. Well, it turns out that right now, we've been calling big A of X. Now, I think in your book, they put a little F like that. They call it big A, meaning the area under F, but we don't write that very often. So when they write big A is equal to and they do it like this, little f of t dt, the key is little f here, then the area function is the antiderivative. So tonight, before you go to bed, say that over and over. The area function is the antiderivative. The area function is the antiderivative of the function that's inside of here. The area function is the antiderivative. So later on, we're going to see this. We're going to see this kind of thing. We're going to see this kind of definition. Because why not, right? Big F, we already have called the antiderivative of little f. So we'll see big F or big G or big H here. Actually, in your homework that I assign tomorrow, and we'll do some in class, that's what we'll call it. Why not? I mean, that's what it is. It's the antiderivative. Pretty amazing, though, isn't it, that happens. That all those connections that we wrote about in the chart, about slope, they all have to do with slope. When the slope's positive, the original graph's increasing, right? All that makes sense. But now you do this bit with area, and all of a sudden, those same connections show up. Now, maybe it's not so surprising, because the first or second day of class, we talked about this. When you do slope, you take the y values divided by the x values, right? When you do area, like in a rectangle, what do you do with the y and x values? Multiply, right? Like length times width, like the height, the width. So it really isn't that surprising, maybe, that area, and this is what I guess Ms. Bishop maybe talks about a little bit with area in physics class, so I don't know if you guys have that. So the first block was telling me that she had already talked about that derivative or slope and area kind of connection. So maybe it's not that surprising that they kind of have this relationship, this kind of inverse relationship there. Maybe it is expected a little bit. All right, so let's take a look at what one problem on your homework is going to look like. It'll be a pretty short homework assignment tonight. There's one problem, number 2, that's going to look just like what we're about to do here. Okay, and then there's 3 through 11. The rest of the problems are going to give you, now listen to this, they're going to give you, on 3 through 11, they're going to give you a little f graph, and then they're going to ask you questions about big A, the area function. Well, what kind of questions are those? Those are chart questions. They're just going to be chart questions. Here's little f graph, and they're going to ask you about big A. That's just like chapter 1, when we gave you an f prime graph and asked you about f. They're just going to be chart questions. Okay, now, I would like for you to think about them in terms of area instead of slope, to just get that mindset going, but at the end of the day, they're just chart questions. So like when we were saying that was concave down, why? Because we were picking up smaller chunks of area. Now, when we were doing slope, we said that it was because the slopes were, it was concave down because the slopes were decreasing. The slope was, 2, and then 1, and then 1/2, and then 1/3. The slopes were decreasing, so therefore it was concave down. Well, now, the area graph was concave down because we were picking up it was 2 different ways. We were picking up smaller and smaller chunks of positive, and then we started picking up bigger and bigger chunks of negative. And that's why it was concave down. Okay? So thinking of it in terms of area, but at the end of the day, they're just chart questions. Okay, so this is very much like number 2 in your homework. All right, so let's talk about notation for a minute. Notice I used little f and I put an x in there. Oh my God, I can't put an x in there. Oh wait, or can I? Can I put an x in there when it's up here? Yeah, where can I put an x in? When it's down there. So notice they put little f of t dt. Well, that's fine, but here's how this problem is sometimes given. Instead of given like that, sometimes it's just given this way. 2 to x, and instead of little f of t here, they put what? No, they don't put x plus 3. They put t plus 3, dt. This and that is the same information. Those 2 things are the same information. They're telling you that this is little f, so the thing inside the integrand is always little f, at least for our work right now. This thing in here is little f, but when we put it in here, it's got to be with t's. When we write it out here on its own, we can use x's or German short hairs or w's or whatever we want. It doesn't matter. Okay? When we put it in here, we can use whatever we want, just not that. Just not that. Okay? All right, so we understand what's going on. So now I'm going to graph over here little f. So what does little f look like? It's a line, goes up 3, slope of 1. I don't care if you think of that as t plus 3 or you think of that as x plus 3, it doesn't matter. It's the same line, whether you're thinking it as x plus 3 or t plus 3, it doesn't matter. That's little f. Okay? That's little f. All right, and we're supposed to do the area, so this is going to be much like you had to do on your packet for today, where you had to draw a picture and find the area. Okay? The difference is we're doing the area from 2 to x. We're not doing the area from 2 to 4 or 2 to 5. We're doing it 2 to x. That means your answer is going to end up with x's in it. Watch what happens. So we do the area from 2, so let's put our left endpoint in, right there. And then let's put our x over here somewhere. Doesn't matter. I usually draw these little arrows just to remind myself that that is a changing value. That's going to slide. Think of the orange area. Think of how the orange area slid back and forth. Okay? And so this area right here is the area I'm looking at. But that's going to change. Okay? That's going to change as we go along. Now, remember, x is the right endpoint. Is it possible that x could slide over to this side? Sure, it could. Right? If I ask you to find a of 0, I'd be asking you to find the area from 2 to 0, right? And that would be negative area. This area here would be negative area because we're going backwards. So we could put the x there, but it just complicates things. It doesn't make any difference. So let's just leave it over to the right. It makes it easier. All right, so what is this area? Well, what shape is that? It's a trapezoid. So we need, so a of x is going to be the area of this trapezoid. So the area of a trapezoid is 1/2. And then we take our two bases and add them together. So here's this base right here. How much is that? How'd you get 5? Yeah, and can't you just plug it into this, right? Same thing. So we can just plug a 2 into this, right? 2 plus 3 is 5. So yes, this is 5. Okay, so that's 5. Plus, now what's this base? Oh yeah, that's trickier. Say it again, Cody. That's x plus 3. Because what is this side? This is an x plugged into the line function. This was a 2 plugged into the line function. Then this one's got to be an x plugged into the line function. Oh, well, that's x plus 3. So that side is x plus 3. It makes sense. It's not a fixed number because it's going to change. When I slide that around, it's going to change. So that's going to be x plus 3. And then we got to times that by this base down here. No, x minus 2. It's this minus this. If this was at 8, that would be a distance of 6. 8 minus 2. So it's x minus 2. So let's put that all together and simplify it a little bit. This is x plus 8, and this is x minus 2. So FOIL would tell me that that is going to be x squared plus 6x minus 16. And then if I distribute that 1/2 through there, that tells me that it's 1/2 x squared plus 3x minus 8. Wait a minute. Now some of you guys had already thought this through. Look at that equation. Look at that answer for the area. What do you notice? It's a parabola, but look at the original. Little f. See, now you guys are all good with the chart stuff and antiderivative, but I'm not sure you were expecting that. But you should have been. Didn't we say that big A is going to be the antiderivative of little f? Right? Isn't that what we said? Well, look what happened. What's the antiderivative of little f? What's the antiderivative of x? 1/2 x squared. What's the antiderivative of 3? 3x. And then y to minus 8? The plus c. So I don't know. Were you expecting that? I mean, when we started this problem, I don't know if you were. Maybe you were. That's good. But that's There we actually see it in equation form. We saw it in chart form. We saw it in graph form there with those other ones. Seem to make sense. Fit all those chart things we talked about. But that to me is amazing too. Just like when we did the definition of derivative, f of x plus h minus f of x all over h, and x cubed came down to be 3x squared. It's like, really? It's that easy? All we got to do is take the power and bring it down? That's it? That's a derivative. That's a slope? Wow. This is kind of the same thing. It's like, you're kidding me. This is a trapezoid. I just did a trapezoid. And it came out to be the antiderivative. Unbelievable. And then we'll talk about the plus c. Is that what you were going to ask about?
Is there a way to not do all that?
For sure. Because we've already done it. But we'll talk about that over the next couple of days. For sure. Yes, we're going to do this some more tomorrow. You're going to do this a little bit of your homework today, a little bit tomorrow, but it's kind of like doing the long way of the derivative. We're going to do it a little bit, but then we won't have to do it after that. Okay? But it's just amazing to me to see it, and I think it's good for you to work through several times and go, you're kidding me. The area of a trapezoid, boom, 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 came out to be this. Now, there's a minus 8. That's the plus c. What do you suppose would have happened? What would we change in this problem to get a different c, do you suppose? The x value is already changing. The x value is sliding back and forth and already changing.
Like from 2 to 5.
So what value? The left endpoint. Remember, we just picked the left endpoint out of thin air. They just picked a 2. What happens if you pick a new left endpoint? Let's say you picked a 1. How would this picture look different? This part would still be there, right? That's the part that gave us all this. But if you picked your left end of 1, what's the difference in that picture compared to this picture? It would just be the little piece of area from 1 to 2. Think about that. Isn't that a constant? Isn't that a fixed piece of area? The only difference between the interval that goes from 2 to x and 1 to x is that little piece of area from 1 to 2, which is a constant. So, and then I always say, I was going to save it for tomorrow, but I can't wait. Okay, so let's take this point. Remember when I slid the x, right? Let's plot all those points. So that's that, right? So there's our area function. Antiderivative, not a surprise, it's a parabola, right? Because that's a linear function, that's x plus 2. So my guess is this is 1/2 x squared plus 2x plus some c, right? So what should happen if we grab and slide this left endpoint? What should happen? Does it get tighter? Does it squeeze? Does it get skinnier? No. What's the plus c do? Isn't the plus c just the vertical shift? So if everything's, it doesn't be embarrassing, it doesn't work. If I move the left endpoint, the left endpoint determines what the c is. The left endpoint determines what the c is. And we'll talk more about that tomorrow. But that, because all it changes, if you move the left endpoint, like I said on that other picture, instead of going from 2 to x, you go from 1 to x. Well, the only difference between those two is that fixed piece from 1 to 2. That's a constant. And so that's the only difference between the different ones is the plus c. All right, so for your homework, I'll leave this up here, and you can get a good start on it so you have this to refer to. We're going to go 5.2. We're just going to do 2 through 11. It's not going to be very long because there's just a lot of big-time concepts here to try to shake out in your head. But because to be honest, at the end of the day, it's kind of like the long way of doing the derivative. There's the concept and the understanding behind it, which is going to come to play a big role all the way along. But when it comes to actual problems to work, this whole concept of it being the antiderivative is what we're really going to do. And Cody says, are we going to be able to find the c rather than have to do all this? And for sure we're going to be able to, right? That's why it's going to be so important to do antiderivatives. That's why we have a gateway test coming up. But 5.2, 2 through 11. So number 2 is going to be just like this. So it'd be good to get a start on that right now. 2 is going to look just like this. Then 3 through 11 is that chart thing I was telling you about. Okay? And so those should be pretty easy, actually. But maybe not. Maybe this whole idea of area is just still kind of dancing around your head and trying to put it all together. So, I guess what I'm saying is don't make it harder than it is. It's really just a chart convention. Okay, the area is the antiderivative. Area is the antiderivative.